I just want to say something about the schedule. So for today, we have the remaining two talks for today are both an hour and a half long. So this talk will be from now until 12:30-ish. I think Louis has like a possible intermission point, like around 45 minutes in, and then if you need to like get up and stretch your legs, you can do that then. If you want to run away, you can also do that then. That's the plan. So we're very happy to have Louis Golowich speaking today about some exciting progress maybe towards a quantum PCP. This is actually going to be the first of two talks this week about progress towards quantum PCP. So it's a very exciting time to be alive. So yeah, so I guess without any further ado, take it away.
Thanks, Anand. So I'm talking about fault tolerance, like fault-tolerant computation against adversarial errors, and its application to PCPs. And this is based on some joint works with Anurag, Nico, Umesh, and Quinn. Great. So what is a PCP, or it stands for probabilistically checkable proof? At a high level, it's a way of robustly verifying computation. So if we have some computation, some circuit, and we want to answer the question, does there exist a satisfying assignment to the circuit? Meaning, does there exist an input on which the circuit outputs, say, all zeros? A PCP gives us a way of compiling the circuit into a proof with the key property that this proof is like probabilistically checkable or locally checkable. And what that means is that we have kind of a bunch of like local checks. Each of these local checks just queries a very small, like a constant number of bits in the proof. And based on this constant number of bits, like each of these local checkers determines like, yes, I think this circuit does have a satisfying assignment, or no, I think this circuit does not have a satisfying assignment. And the key property is we want most of these local checks to output the right answer. So like if there does exist a satisfying assignment to the circuit, then we can compile that into a proof where kind of most of the local checkers, most of the local checks output, yes, there is a satisfying assignment. And if the circuit does not have a satisfying assignment, then there's no such proof that will convince most of these local checks that there is a proof. So at a high level, this is what a PCP is. It's just a way of compiling a computation into a proof that's locally checkable. And this local checkability property we can think of as like a robustness property. Because this local checking is just inherently robust. If we corrupt, say, even like a constant fraction of the proof bits, or we also corrupt like a constant fraction of these local checks, since everything is local, like still kind of as long as this constant fraction is sufficiently small, the vast majority of our checks will still give the right answer. So this local checking is like inherently very robust. If we, for instance, if we were to sample just like a very small number of these local checks and just check whether they give yes or no, even if there's like some reasonably high number of errors in the proof, we'll still probably get the right answer. So that's the statement of what like a PCP gives us. If you think about it, it's kind of striking. Like when we're checking a proof like in a paper, we have to read through the whole paper, kind of check every single line carefully to see if it's correct or not. Whereas this is saying actually you can check the output of a computation by just reading an appropriate proof in just like a constant number of locations. So it sounds pretty striking, and indeed, like the fact that PCPs exist classically is kind of one of the celebrated results in classical complexity theory. It's like a really beautiful, deep theory. And it remains open whether you can do the same thing quantumly, whether we can compile a quantum computation into this sort of a locally checkable proof. So one main motivation for this talk is kind of making progress towards this quantum PCP conjecture. And the way we're going to attack that is by asking a variant of the question of whether we can robustly verify computation, which is whether we can robustly perform computation. So what does that mean? Now I'm still going to start with some circuit, and I want to know if it has a satisfying assignment or not. But now instead of compiling the circuit into a proof that's supposed to convince us about something about the output of the circuit, I'm just going to compile this circuit into another circuit that robustly just simulates the original circuit. And what I mean by that is if in every time step of this new circuit, we allow like kind of a constant fraction or almost a constant fraction of the bits to be corrupted, or the qubits to be corrupted, I still want to get the right output from this compiled circuit. So we've kind of gone from like robustly verifying the output of a circuit given a proof to just robustly performing the computation itself. Now we're not even given any sort of proof to help us. And so naively, this might seem impossible because, say, if we have like one corruption on the input, that could totally change the output of the circuit. So that's why we need to allow ourselves to like receive an input encoded in some like error correcting code, and also allow ourselves to output the output of the circuit encoded in some error correcting code. But once we do that, then this statement makes sense. Then we can hope to like robustly perform the computation and, even in the presence of a lot of errors, still output an encoding of the correct output up to some like decodable error. So aside from like the general kind of the general idea that robustly performing computation sounds similar to robustly verifying computation, as I'll describe in a couple slides, it turns out that like robustly performing computation is in some sense strictly stronger than verifying computation. Kind of up to some polylog factors, if we can robustly perform computation, we can use that to get PCPs, to get robust verification of computation, at least in the classical setting. Great. So what are we able to show? We basically answer this question, can we robustly perform computation in the affirmative in both the classical and quantum settings? So in the classical setting, we construct a classical robust computation, or we call that like a fault-tolerant scheme, which compiles an arbitrary circuit here. We'll call this the logical circuit, like the circuit that we want to compile, into a physical circuit, like the physical circuit we actually run under noise, with fairly small space and time overheads. So if our original circuit uses time or has depth t and uses space or width bar t and bar n, then our physical circuit has time usage that's only like subpolynomially larger than the original time usage, and space usage that's again just a little more than linear in the original space usage. And the key fault tolerance property is that the physical output, the kind of output of our physical circuit, is correct, so it's decodable to the true logical output whenever the adversary arbitrarily chooses and corrupts an almost linear number of bits, like n to the 1 minus little of 1 bits in every time step. So the adversary is like a very large and almost linear number of bits that they're allowed to corrupt in every time step. And we're still able to kind of compute the correct output under this pretty strong error model. So, if you haven't kind of seen fault-tolerant computation before, this might just kind of look like an arbitrary result. It might be a little unclear kind of like how strong this result is, if we should expect it to be true or not. So maybe just to give some context, so if we kind of tweak the model a little bit, like we kind of allow ourselves to abort if we detect too many errors, but roughly keep the result the same, we can improve this n to the little of 1 down to like just a polylog loss. And then as a corollary of that fault tolerance, this fault tolerance scheme, we actually just immediately get a new construction of classical PCPs up to polylog factors. So the true classical PCP theorem is like a constant soundness PCP, like it's robust like a constant fraction of corruptions. If we reduce that constant to a polylog, then all of a sudden we can recover like this polylog weaker PCP theorem just as a direct corollary of our fault tolerance scheme. So I guess this is interesting for a couple reasons. One is that it's showing that there actually is really something going on with this fault tolerance scheme, because PCPs are, even polylog weaker PCPs are not easy objects to construct. They're like pretty interesting, pretty structured objects. But the other reason this is interesting is fault tolerance so PCPs are not very well understood quantumly. Fault tolerance is something that's highly studied quantumly, so that's maybe a hint that actually this approach to constructing PCPs should be quantizable.
Can you explain more in detail how do you get this classical PCPs?
Oh yes, thank you. So in like 2 slides, I have a whole slide, so I'll go exactly through that.
Wait, another question. So, is the exciting thing here just that you're able to deal with adversarial error at all, or is it like the actual like parameters, the sizes and stuff, or like what was like known prior to this, I guess?
Yeah, also a great question. So sorry, I'll have a related work slide later, but roughly speaking, what was known is you can withstand, like it was previously known how to withstand like square root n adversarial errors per time step. Or actually, if you allow the space usage to blow up, you could get like 1 over poly n. But getting from 1 over poly n fraction corruptions to like 1 over subpolynomial, that was somehow like the real barrier. Like even just using a repetition code, like a really simple fault tolerance scheme, can get you resilience to 1 over like inverse polynomial fraction errors. Yes.
Sort of extending that question, what is the goal to get the actual QPCP?
Oh yes, for QPCP.
Yeah.
So I'll get into that a bit more. Roughly speaking, we first want to quantize this classical fault tolerance scheme, and then there's one additional missing piece too. Cool. Yeah, so I'll go into more detail in all the things on this slide later, but first I'll just kind of state our main quantum result, which is basically we're basically like taking this classical result and replacing classical with quantum. I'll just highlight in blue kind of what changes going from classical to quantum, because actually not that much changes in like the result statement. So now we're compiling a logical quantum circuit into a physical quantum circuit. The time overhead is again like subpolynomial. The space overhead, it now jumps to a larger polynomial, so now the physical space usage is like the original logical space to the power of 5 roughly. But that's kind of fine in the PCP setting. We'll just have longer proofs. And again, we have this fault tolerance property that we correctly perform the computation in the presence of like an almost linear number of adversarial errors in every time step. The one additional kind of technical assumption we need here is that we have to allow the physical quantum circuit to like run some free noiseless side classical computation. I won't say too much about that because it doesn't seem super fundamental. You can kind of remove this in the PCP setting where you're allowed to only detect errors instead of correct them.
You don't have to have that.
Sorry?
You don't have to have this in quantum components.
Oh, sorry. I meant we need it in our scheme. No, that's a good point. Yeah, and there are like I guess your original like quantum fault tolerance scheme doesn't have this, but we're not able to remove the classical computation in our scheme at this. So yeah, actually, it is an interesting question to totally remove this side classical computation. Yep.
So what was known about adversarial errors in the quantum setting?
Roughly the same as classical. Like you could correct inverse polynomial. Actually, it's worse, I think. So classically, you can use a repetition code and like correct 1 over n to the epsilon as your space usage blows up. Quantumly, I think it wasn't known how to get better than like 1 over n to the 1/3, or sorry, 1 over n to the 2, like 1 over square root n roughly.
What was the ends? Am I comparing the ends of the encode? Like, n over n to the 5 is still.
Oh, sorry, yeah. So we always want these to be polynomial related. So if you just think of it as inverse polynomial, then they're kind of the same. But quantumly, even for big N, I think like for the physical space usage, it wasn't known how to protect against more than like cube root n adversarial errors per time step. Yeah, cube root big N, like cube root the physical number of physical qubits. Cool. And so the motivation of PCPs, and indeed assuming one conjecture that is still wide open and still very interesting, then kind of this sort of quantum fault tolerance scheme could give us some quantum PCPs with like non-trivial parameters, so like with subpolynomial soundness. So again, it's still not like, it's still somewhat far off from constant soundness, but kind of if we had this conjecture, then we could get like some sort, like maybe like the first like non-trivial PCPs, because inverse polynomial soundness is like trivial, like kind of inverse polynomial soundness is what you get just from QMA without like adding any PCP machinery on top of it. So in some sense, this quantum fault tolerance scheme is like addressing one of two bottlenecks towards constructing quantum PCPs. And in like 2 slides, I'll describe exactly how these things fit together. Yeah, I will also say, just as a side remark, like I'm saying could give here because there's some technical details in like massaging a fault tolerance scheme into the setting where we can apply this conjecture, but yeah, it seems like the real bottleneck now is just this conjecture. Cool, so.
And you'll tell us this conjecture, right?
Yep, yeah, that's coming up next. Yeah, so I will first describe now how we can go from a classical adversarial fault tolerance scheme to classical PCPs. Then I'll describe the quantum analog of this, and the bottleneck in the quantum analog is this conjecture, which I'll describe. So how do we go classically? So we start with this question of just, does there exist a satisfying assignment, an input to some circuit, an input to the circuit giving output 0. And we want to compile this logical circuit, this circuit, into a proof that should convince us, like a PCP proof that should convince us that there does or does not exist a satisfying assignment. And the first step is we just compile this general circuit into a log depth circuit. And this is actually just a pretty direct, like a pretty simple reduction. We just kind of create a new circuit where the inputs to this new circuit are the wires, like the space-time locations of the original circuit. And then all the new circuit will do is it first goes through every gate in the original circuit and checks that the gate's inputs are consistent with the gate's outputs. So that's like a local check, because it's just checking kind of 2 inputs and 2 outputs for every gate. And then we just kind of take the AND of all of these individual gate checks, and that's like a log depth circuit, because we're just computing the AND of like a linear number of gates. So we end up with like a log depth circuit where there's a satisfying assignment to this log depth circuit, kind of if and only if there's a satisfying assignment to our original arbitrary depth circuit. Great. So next, the key step is the next one. We take this log depth circuit and just run our fault tolerant compiler on it. And we get a fault tolerant version of this same log depth circuit. And assuming our fault tolerant scheme is like polylog depth overhead, then this new scheme now is polylog depth. And what's nice now is like we're allowed to, because the circuit's fault tolerant, we have the same, we like have the same question, like just like does there exist a satisfying assignment to this polylog depth circuit? If so, then we know there's a satisfying to the assignment to the original circuit. But the key point is this circuit is fault tolerant. So now actually we're allowed to run the circuit noisily. We now just want to know, like, does there exist an approximately satisfying assignment to this circuit when we like run the circuit noisily? And because of that, if we kind of take this polylog depth circuit and construct a CSP out of it, where the CSP just kind of has variables corresponding to the space-time locations, and so kind of similar to what we did up here, and we have constraints checking that each gate was executed correctly, all of a sudden, like a polylog soundness PCP just kind of pops out. And the reason, so the PCP proof is just a transcript of the execution of this polylog depth fault tolerant circuit. And then our PCP verifier just kind of samples a random gate or looks at any individual gate and checks that that gate was executed correctly. The point is, if most of these checks are satisfied, it means that this circuit was executed mostly correctly with like a small number of errors. And since it's a fault tolerant circuit, that actually means that it outputs the correct value. So that means if we have like an approximately satisfying assignment to this CSP we got at the end, if our PCP proof accepts with high probability, then we actually know that this fault tolerant circuit ran correctly, which means that we actually know that the underlying log depth non-fault tolerant circuit does have a satisfying assignment, which then means that our original circuit has a satisfying assignment.
So where's the
sorry.
polylog and the soundness come from in the final version?
Right. So
Relate to the depth or the error rate or both?
both actually, yeah. So it relates to the depth because if we wipe out a single time step, since it's a polylog depth circuit, that's 1 over polylog fraction of the total proof bits. And also our error resilience in our fault tolerant scheme. Our fault tolerant scheme can only handle errors on 1 over polylog fraction. So it's like a product of 2 polylogs.
I think I followed at least the first zig across, but so am I correct? This log depth circuit is kind of it's very triangular, right? It like comes to like a point and there's one accept gate.
Yeah.
What happens to that triangular setting when you go here? Like, does I don't know
Yeah.
what to say. Maybe you know what I'm saying.
Yeah, that's a good question. So it actually, it untriangulates. You can think of it as, like, we start with an encoding in a high rate code, and we end up, our output code is actually different from our input code. Our output code can be just like a repetition code. So it's like, our input code as like very high rate is like n bits encoding like order n logical bits. Our output code is like still n physical bits, but now encoding like one logical bit.
I see. So there are many, like, on that final layer, there are many bits that tell you whether the circuit was going to output 0 or 1. Not
Yeah,
just
exactly.
Okay.
Yes, and then
I have sort of a silly question. So you can compress this log depth circuit to a constant depth circuit if you allow for post selection. Is there any hope that that could like zig all the way through here and help you, or?
sorry, I'm not familiar with this. Is this?
It's more or less the exact same reduction you've shown, but you basically post select on all of the like input wires agreeing from one gate, like agreeing, or the output wires from one gate agreeing with the input wires from the next gate.
Oh,
I think it's not known how to make the selection circuits adversarial.
That's what I would have guessed, but I wanted to check. Yeah.
wait, sorry. So this is still classical? Or are you talking?
Yeah, this is classical.
Wait, so if you classically post select?
You can compress this, like there's a set of wires you can post select on, like say I'm going to post select on all these wires being 0. Those essentially like the checks to make sure that all your gates are consistent, and then the rest of the circuit is just like the rest of the wires are just simulating the rest of the circuit. This can all be done in constant depth, but you have to post select on those sort of output wire, input wire checks like matching. So then you have like a bunch of like 0 bits that are post select to 0. Then you're sort of checking if there's a satisfying assignment.
I see. Oh, I'm not sure I 100% follow, but I think it's the answer that it's on how to make that.
Okay.
Yeah, I guess one other comment. So another thing, if you actually don't take the and you just allow this logical circuit to have, like this circuit to have many outputs, then it's already constant depth. Like we could just not take the and. But yeah, then it's still not, like our fault tolerance scheme will introduce a polylog overhead anyways. Yes.
So even when you have like constant overhead for tolerance, the first step is going to constant log, right?
Yes. So I should say, so the last thing I just said, we could actually not take the and like have this be constant depth. And so you could actually theoretically hope to not lose the log. If you just allow your circuit here to have like many outputs, and then your fault tolerance scheme also has many outputs. Cool. Yeah, so this is the classical mapping. So you can see kind of the top and bottom arrows are kind of just like definitional. They kind of follow it immediately once you look at things in the right way. And kind of all the heavy lifting is done by the fault tolerance scheme. So quantumly, we can try to do the same roadmap. This is what this work by Anurag, Nico, and Quinn, this ABN 24 paper did. And we'll have the same steps, but there will be kind of more unknowns. So again, we start with like QMA, and like a QMA complete problem is just whether there exists a satisfying an input, so an input that gives output 0 with high probability to some quantum circuit. And the first step, again, is kind of similar as last time. We want to compile the circuit to a new log depth circuit such that this log depth circuit has a satisfying input if and only if the original circuit has a satisfying input. This is already harder than the classical one, but it turns out it's still not that hard. Like the ABN 24 work showed how to do this, like do this compilation step using like a Feynman-Gatayev circuit to Hamiltonian to construct a Hamiltonian from this circuit, and then using the detectability lemma to just kind of do a similar thing as we did in the classical setting, measure all of the Hamiltonian checks in a constant depth circuit, and then take the and of all of them. So the first step is still okay. The second step, we just, again, run our fault tolerance scheme. So now we need a quantum fault tolerance scheme. And now we have this quantum fault tolerance circuit. I should say, so our quantum fault tolerance scheme I mentioned has like subpolynomial depth. So in that case, this would be like a subpolynomial depth circuit.
And
So,
it should be robust to what? Adversarial noise, exactly?
oh yes, thank you. Yeah, it should be robust to adversarial noise.
But to what value? Like,
Oh, to,
like,
right. So if we wanted a polylog, like an inverse polylog soundness PCP, it should be robust to inverse polylog fraction errors. If we want a 1 over n to the little of 1 soundness PCP, then it should be robust to 1 over n to the little of 1 fraction adversarial errors. And yeah, that's just by, yeah, if you kind of trace through just backwards what you get, then that's, yeah. Yeah, but based on what everyone was asking, like if you want truly a constant depth, like a constant soundness PCP, you need to do more work because we're always losing a log from this log depth circuit. And then the final step is to map this polylog depth fault tolerant circuit to a PCP, and this means like we want now a quantum CSP or like a quantum local Hamiltonian, and we want the property that kind of any approximately satisfying assignment to this quantum CSP, so any like low energy state of this local Hamiltonian should encode a low error execution of this fault tolerant circuit. So this is like exactly like in the classical setting where we had a PCP that just directly encoded like transcripts of the circuit here. Now we want a local Hamiltonian whose low energy states encode like noisy executions of this fault tolerant circuit. And so in the classical setting, it was almost just immediate getting this final step. In the quantum setting, it's an open question, which was kind of introduced by this ABN work. And as I'll describe in the next slide, they gave like a very interesting construction, like a candidate construction for compiling a circuit into a Hamiltonian that satisfies this property. But it's still an open question to kind of prove the soundness, to prove that all the low energy states of this Hamiltonian truly encode low like bounded error executions of this circuit. I should say like kind of known circuit to Hamiltonian is mapping like the standard like Feynman-Kitaev circuit to Hamiltonian, which we used up here, kind of are known not to have this soundness property. So there do exist like low energy states of like the Feynman-Kitaev Hamiltonian that actually don't correspond to low error executions of the circuit. Yeah.
Sorry if I can harp about triangles again. What happens in the untriangulation here? Because like quantum codes have no local information, right? So the repetition code. So what's the magic?
Yeah, that's a great question. So it seems like what you want to do is now you actually, the answer changes from the classical case. And you actually can do this classically too. But now we actually do have a triangle in our fault tolerant circuit. And essentially we want to, in every time step, we want to like shrink our code by say a constant factor, but then double the weight of the Hamiltonian checks that we ultimately impose there. So kind of we have fewer and fewer qubits, but each qubit is more expensive to corrupt because actually we get to choose the cost of a corruption
So
by weight.
like with constant weight, you check the last row and then like, okay, 1/4 and like some zeros.
Exactly, yeah.
Okay.
Unfortunately, as I'll describe, like our fault tolerance scheme has pretty flexible codes, so actually just like slowly shrinking a code down to a single qubit is actually doable. That's not a problem in fault
Do you
tolerance.
think this unbalanced kind of Hamiltonian is necessary, or do you think you could massage it so you can do this untriangulation honestly?
That's a really good question. I'm actually wondering this myself too. Cool. So what is this conjecture? So the conjecture is just that we can map, it's what I said, we can map a quantum circuit to a local Hamiltonian for which every low energy state of the Hamiltonian encodes a low error execution of the circuit. And this work by Anurag, Nico, and Quinn gave a candidate construction. And they made some nice progress towards proving the conjecture. So what does their construction look like? So let's start with the circuit they want to compile into a Hamiltonian. The first thing that we'll do is we're going to add a small ancilla system at every wire, so at every space-time location in this circuit. And intuitively, this small ancilla system is just it's gonna record the state of the wire, like the record whatever state is in that wire at that space-time location. So if we just think about the classical analog for a second, classically we just kind of do a C0 gate into a fresh ancilla initialized to 0. So we're just literally like copying the bit in the wire into our ancilla system. And this is kind of very similar to if we recall what we did in the classical setting to compile a circuit into a PCP. We had this step where we just kind of write down the transcript of the execution of the circuit. And that's literally what this is doing. We're just writing down like the value of every wire at every time step. So quantumly, it's known that we actually can't do the same thing because of the no cloning theorem. Kind of if you were to try to write down the quantum state in a given wire, that would necessarily like totally just corrupt. Like you could copy the quantum state to a fresh ancilla system, but then that would like totally corrupt the original wire. So the output of our circuit would be totally corrupted. So we can't do that. But the ABN work had a really nice observation that we can do something almost as good. We can kind of gently record the state of the wire. So we can write down something that has like a little bit of information about what's in the wire. And this will like, it won't totally corrupt the wire, it will like mildly corrupt the wire. And like strictly speaking, like what is a circuit to do that? It kind of has two ancillas and each one is like a little bit off from a 0 or plus state and we do some C0 gates. But really, this is just the circuit that implements a very weakly depolarizing channel, like an epsilon depolarizing channel on the wire. So like kind of epsilon corrupt the wire. And then the ancillas are like a purifying system for this depolarizing channel. So kind of by information disturbance, we're like slightly depolarizing the original wire, which means that we're recording a little bit of information about the wire into our ancilla system. And now if we run the circuit, we'll run like a slightly noisy version of the circuit, a version of the circuit with a little bit of coherent noise at every space-time location. But the key point is that now at every space-time location, we also have recorded some information about the state of the circuit. Yes?
Can you just go slightly slower and explain what is this small gadget is doing?
Oh, yeah, sorry. So the classical one is just adding the bit into a fresh ancilla, so we're just copying it. The quantum one, so like there's these two ancillas. One we introduce to 0 and then epsilon, 0 plus epsilon times the 1 state, so mostly 0, a little bit 1. And we perform a C0 from that into the wire. So that just with a small amplitude, it adds a 1, it adds a bit flip. Most of the amplitude just leaves it alone. So it introduces like a low probability, like a low amplitude bit flip. And then this other qubit is also introducing like a low probability or a small amplitude phase flip. So we combine these and we get like some weak noise, some weak like depolarizing noise. Where like we kind of weakly both corrupt the bit and the phase value. And then our Hamiltonian will kind of be similar as in the classical setting. We'll just kind of check before, we just look at every gate and we look at the ancilla systems on either side of that gate and we check that the ancilla values before the gate are consistent with the ancilla values after the gate. So like the ground state of this final Hamiltonian will encode a perfect execution of our new noisy circuit. But this noise is actually stochastic, like it's not adversarial noise. This is just noise that is like weakly depolarizing at every location. So there's a difference from the classical setting. Now if we have a true ground state of our Hamiltonian, it is a noisy execution, but it's like very well behaved noise. It's just like this weak depolarizing noise at every location. And so what we'd want to show is that every low energy state, so states that aren't ground state but still decently low energy, correspond to low error executions of the circuit. So executions of the circuit that now have this weak depolarizing noise and some adversarial errors. But it's still not known that there couldn't be some low energy state with some just totally crazy noise. So that's kind of what we'd still need to prove with this conjecture.
Can you say more about the counterexample that you said?
Against Feynman-Kitaev.
I'm sorry?
The counterexample, sorry, which counterexample?
You're saying that in some place, I didn't catch, that there is that you do have low energy states that don't correspond
Oh,
to
like
the
for the Feynman-Kitaev.
Oh, that you meant Feynman.
Yeah. Yeah, so actually I don't recall exactly how you construct it. I think, so Feynman-Kitaev goes kind of one gate at a time.
I guess you can do some kind of a quadratic, like a Zeno effect that you can.
We just introduce a fault at one point in history.
Yeah, okay, yeah, it's not stable in various ways.
Oh yeah, that should work. I mean, you can also look at like variants of Feynman-Kitaev with like a bunch of local clocks, but you still have similar.
Can you repeat the idea, Louis?
Oh, so I think what Umesh says is you just introduce, since Feynman-Kitaev will always blow up the depth of a circuit because it does gates one at a time, you just corrupt.
Like you just stop it at some time, right? And then
You can just use an all zero state as a counter example. Like all zero on the clock and all zero on the data. So that state will only be checked by the first propagation term in the Hamiltonian. It will only violate that term. Because all the other terms will get logical.
Right. Yeah, so I think to summarize I think correct me if I'm wrong, but I think it's the core issue is that Feynman-Kitaev, it kind of implements gates one at a time. So you can just kind of, you mess up one time slice and that's only an inverse polynomial fraction of the entire like number of Hamiltonian checks. But if you corrupt like one time slice, you can just totally change what happens before and after that time slice.
How is this circumvented here?
Right, because this Hamiltonian in a low depth circuit, if we corrupt like one entire time slice, that actually has many gates because our circuits are very, so we have like very low depth circuits with like very, like very low depth circuits with a lot of space. And here we're kind of, if we just fix one time step and corrupt all the qubits in there, then we're going to violate all the checks that lie in that time slice, which is like 1 over polylog fraction of the total number of checks. Oh yeah, sorry. So maybe another thing is, so Feynman-Kitaev, it kind of like, at every time step, it writes down the whole state, but then just does one new gate. Here, we write down the state at, we parallelize. Yeah, it's like we write down the state at one time step, and then the next thing we write down is the state when we've executed all of the gates in that time step. So we do all the gates in parallel.
So the check is just a local check on one gate, right?
Yes.
I think if it's adversarially, if the underlying circuit is adversarially fault tolerant, then you're good, right? Because
Yeah, so maybe the confusion is like Feynman-Kitaev is also only checking, like it only checks one gate at a time.
So yeah, like Feynman-Kitaev, I check one gate at a time. But here it seems like I'm checking one gate at a time.
But
Yeah, so I guess Feynman-Kitaev, it checks one gate at a time, but like for every time step, like you have like t tensor the state at time t, and then you have t plus 1 tensor the state at time t plus 1. And you need to t has to, like, from going to t plus 1, only one gate gets executed.
Right.
So the total number of t's is like n. Which means that if t tensor the state at time t, and then we change t plus 1 tensor a totally different state, that actually will only corrupt one out of these like n different checks.
It's the fact that I'm recording the times.
Yeah, like in Feynman-Kitaev, you record it after every individual gate. Here we kind of only record it after every layer of gates, kind of.
I guess maybe a way to say, like in Feynman-Kitaev, you only check the time steps that are in the state you were given, in the superposition of the state you were given, right? It's like if your thing, as in Quinn's example, only had weight on time step 0, you're just never going to do any checks that have to do with the later gates, right? But like here, the checks for the later gates are always applied because you always have to put some qubit in that thing.
Right.
Does that answer?
I guess the history state is eminently puncturable, whereas this thing, to puncture it, you've got to do a lot more work.
Yeah.
Here, you seem to be asking that this circuit Hamiltonian is more than a PCP, like it satisfies some notion of proximity. Not only is a low energy state have the correct answer, but it was also close to the correct answer. And like, is this necessary? Do you think it's any significantly harder to prove than the potentially easier statement of the capacitors for that?
Oh, you mean like any low energy state corresponds to an execution of the circuit with the correct answer, even if?
Yeah. Or like you really think like to get the correct answer, you have to have low energy, low error on every vote.
So I will say, so the conjecture does allow like superpositions of errors on different sets of qubits. So it does allow still like a fairly general class of errors. I guess that is a good point. Like it could be that somehow the right answer is coming out of like a total mess in the middle. Yeah, I think it's interesting. I haven't thought about that. Cool. Great. So this is the conjecture. This is like if you want like the one bottleneck towards getting some sort of non-trivial quantum PCP. This seems like the main bottleneck we seem to have at the moment.
Sorry, one more question about this thing. I feel like I just vaguely remember something about like this doesn't necessarily even reproduce like regular Feynman-Kitaev like is it true that if I just want to prove like the usual statement about local Hamiltonian mean QMA complete, like can I get that from this construction, or do we not know how to get that?
Yeah. You can prove the usual QMA completeness from this.
Okay.
Can you
Constructing.
Can you repeat what you just said?
Yeah, you can prove the usual QMA completeness statement theorem from this Hamiltonian by constructing a low depth.
Yes, you can. So you need to construct a low depth fault tolerance protocol for depolarizing noise, and that suffices to use this Hamiltonian to prove the standard QMA theorem. That's what we have in the version 2 of the paper. Yeah.
That's interesting. I guess like just natively just like apply it to a circuit, like you don't get like a QMA hardness. Like you first do some sort of fault tolerance first.
You don't. So if you, for example, take the original fault tolerance protocol, you would get a polylog depth overhead, and that would only give you inverse super polynomial soundness for local Hamiltonian. So you need to construct some non-trivial fault tolerance protocol to keep the log depth of the QMA circuit.
Thanks.
Cool. Yeah, thanks, Quinn. So this is, I guess all I'll say about this conjecture. Yeah, not all I'll say.
What's known now about the low energy states?
So it's known, I guess, or I guess Quinn could probably answer this better, but it's known like for log depth circuits that it works.
Oh yeah, so the proof of QMA completeness theorem uses the ground state, and in this paper we show some properties of some special class of high energy states. Yes, I don't know if Louis will describe that.
Oh yeah, so like it's known like if you, for instance, there's like a combinatorial version that's known where like if you don't look at like low energy states, but like low error states. So like states that, if you just count constraints that are like at all violated, as opposed to like allowing like a lot of constraints to be a little violated, then like Quinn's paper, like Anurag, Nico and Quinn's paper shows that you do have the desired soundness. So you can get like combinatorial, you get like a combinatorial type of quantum PCP. We actually don't do that out just because like you need to massage the fault tolerance scheme into that framework, and it's just kind of a lot of, like it seems like you could probably get a combinatorial PCP from our results, but we just didn't do out the work purely from like a labor point of view. Actually, I'll say a bit more about the labor at the end. Yeah. Cool. So that's all the PCP motivation. I guess the one other thing I should say is that fault tolerance you can actually motivate without even talking about PCPs. And I think, especially in practice, this is actually arguably even the stronger motivation. So first, there is this foundational motivation, like classical and quantum computation are like, we're saying that they're possible in the presence of like extremely strong adversaries. This is courtesy of Nico, or maybe it is Nico, I'm not sure. But yeah, I guess Levin, like one of these, he's like a prominent skeptic of quantum computing, and he's like, oh, like this, like adversarial errors will put like quantum states in like devilish states of conspiracies, which defy imagination. So like quantum computing can never work. And we're saying, well, actually, like even if your adversary is pretty powerful, like pretty devilish, at least in theory, you still can do quantum computation. So that's one motivation. Maybe this work will make Levin happy. You also have like a much more practical motivation, which is that like good error resilience is actually important in practice. Like all these companies are trying to like develop like fault tolerant procedures to like run on their actual like physical devices, and like whenever they announce like they have a new quantum code, like good things happen to the companies. So like this is saying like maybe we should really be focusing on the practical implications of fault tolerance. And if you look at like what happened in the past with like these good QLD PC codes, which I'll talk about a bit later, like people came with these Nico and collaborators came with these good QLD PC codes, which theoretically were beautiful. And since then, the ideas have like slowly trickled into practice, and now are like really influencing like what all these companies are trying to do in their devices. And the thing is, we don't just want codes; we want whole fault tolerance schemes. So now we're introducing like fault tolerant protocols that like have asymptotically like close to like good error resilience. So maybe this will also like trickle into practice. Cool. So I guess we're roughly due for a break soon. So I might just, is that clock right? Yeah. So I might just give a brief recap. So we give a way of compiling a logical circuit into a physical circuit so that the physical circuit is robust to like an almost linear number of adversarial errors in every time step. We do this classically, and we get some classical PCPs up to polylog factors. We also do it quantumly, and we get like a conjectural construction of quantum PCPs with like subpolynomial soundness. So I think we can break. Maybe I'll actually do one more slide. I'll give a brief just overview of what was previously known. So previously known, it was known how to get both classical and quantum fault tolerant schemes that predict things like an inverse polynomial fraction of errors per time step. Maybe it's not surprising that classical schemes were too weak to construct PCPs because people had to work so hard to construct PCPs. It might be a little surprising if just someone had constructed a fault tolerant scheme sitting out there that actually gives a PCP. And like the key challenge, like the key reason that like more simple fault tolerant schemes don't give what we want is because like a classical approach, like some of the earliest fault tolerant schemes, what they did is just encode each logical bit or each logical qubit in a separate code block. And then they like run some gadgets on different code blocks. This will never work in our setting because it means that errors on 1 over the number of logical qubits, fraction of physical, errors on just like a single code block, which is only 1 over the number of logical bits or qubits. Like errors on a single code block can totally wipe out a logical bit or a logical qubit. And this means that you can always get the wrong answer. So we really will need to like encode all of our bits or qubits into like a single or like a small number of code blocks. So that's kind of just a teaser of what's to come, but yeah, maybe we can break for a minute or two.
Let us resume.
I think so, yeah.
Oh, I guess we'll continue. So we left on this this slide just saying kind of what are the key challenges in getting a fault tolerant scheme that's resilient to like an almost linear number of adversarial errors. And yeah, the key problems are kind of we can't afford to encode logical bits or logical qubits into separate code blocks because then we could just corrupt a single code block and that would wipe out a single logical bit or qubit. And that's a fairly cheap corruption, but it totally could mess up our output. So instead, we need a way of jointly encoding all of our logical qubits into like one code block or a very small number of code blocks, and somehow operating fault tolerantly on this like joint encoding. So almost all fault tolerant schemes that I know of kind of go in two steps. The first step is to construct a memory. So this is to construct an error-correcting code, a way of encoding our logical bits into logical qubits in such a way that we can just correct errors fault tolerantly. So we can like correct errors as they appear and correct them before they appear too much or before they propagate too much. Just correct them faster than they appear. And if we just have a memory, we can kind of, in the presence of noise, we can store a logical state, correct errors as they're appearing, but we can't do any computation. And so the second step is once we have a memory, we then want to show how to perform computation, show how to fault tolerantly execute logical gates on this memory. So we'll go through these same two steps, and I'll first describe the memory. We want a memory that's resilient to like an almost linear number of adversarial errors, and then I'll describe how we perform computation on this memory. Right, so how can we construct a memory that's resilient to an almost linear number of adversarial errors? So we just said we can't encode each logical bit or qubit in a separate block. We need to jointly encode them all in like a small number of code blocks, and each code block has to have high distance. It needs to be resilient to a lot of errors. And it turns out that this is kind of, people actually already know how to do this, both classically and quantumly. So classically, it turns out that like you can take an LDPC code. This is just a code in which there's like a constant depth circuit that can kind of measure some low weight checks. So it's kind of, we have a bunch of low weight, like local checks, each just checks a constant number of bits in the code. And we can measure all of these checks in like some constant depth circuit. And then based on the values of these checks, we can apply a correction, which will correct whatever error had occurred on our code. And like, there's many known classical LDPC codes that support this like constant depth check circuit and then a constant depth correction. And the idea is like, if everything is constant depth, then there's not that much time for more errors to occur and to propagate. So this error correction procedure can actually correct errors more quickly than they appear. So great. So we have classical memories that are robust to an almost linear number of adversarial errors. Can we also get a quantum memory that's robust to an almost linear number of adversarial errors? So it turns out that it is also known how to do this, and we just stick the word quantum in front of what was going on up here. We use almost linear distance quantum LDPC codes, or actually even just linear distance quantum LDPC codes. And there's kind of a beautiful line of work constructing these linear distance quantum LDPC codes. And kind of even more, in an even more kind of exciting development for the purpose of this talk, these linear distance quantum LDPC codes led to the proof of the NLTS theorem by Anurag, Nico, and Chinmay. And the NLTS theorem was kind of like one of the few like stepping stones of quantum PCP that's actually been proven. So this is really indicating that like these linear distance, these good quantum LDPC codes seem like they're kind of exactly what we want. They give us this quantum memory that's resilient to like a linear number of adversarial errors, and they led to NLTS. Actually, in terms of like getting the reason that people like really want to construct these quantum LDPC codes was precisely because they give a quantum memory. As far as I understand, was because they give a quantum memory that's robust to like a linear number of adversarial errors. So we have our memory. Now how do we do computation on it? So fortunately, there's like a whole field studying this. Like there's this whole field of quantum fault tolerance, which somehow is a surprisingly small overlap with like the PCS community, but people have come up with like all kinds of techniques for doing fault tolerant computation on quantum LDPC codes. And this is just like a small random sample. Like, yeah, there's like tons of works doing this stuff. So yeah, people have like all kinds of ways to do basically any gate you could want on LDPC codes fault tolerantly. But it turns out that there's an issue in that actually, as far as we were able to tell, like none of these techniques can withstand adversarial corruptions on like even like 1/square root and fraction of the qubits. So I guess the exception is transversal gates, though for some technical reason I'll describe in a bit, we're not able to figure out how to do like the appropriate transversal gates on these good LDPC codes and like put everything together. But kind of like all of these techniques kind of they don't seem to withstand enough errors for our purposes. So actually we just won't be able to use like quantum LDPC codes. We won't be able to use a QLDPC memory because we don't know how to do the fault tolerant computation and withstand enough errors. So it turns out we're actually just kind of back to the drawing board. Yes.
You mentioned that transversal gates were the exception.
Yes. Yeah, so that's a good point. So as I'll describe in a bit, kind of it's not like we're coming up with things from scratch. We actually do borrow some techniques, like many techniques from like prior works, and actually, arguably, like the work that is like most similar to what our scheme can end up with is like the original like a Hardham Benor fault tolerant scheme from a couple decades ago. Somehow, like yeah, we need to kind of look beyond quantum LDPC codes and kind of look back to kind of some earlier techniques. And like what goes wrong? Like why does everything here fail? Like the core challenge is that we want a memory with like with the ability to perform a fault tolerant like multiplication or Toffoli gate. So like if there's like one gate you want to get universal computation, classically it would be multiplication, and quantumly it would be Toffoli. Toffoli is just like when we multiply 2 qubits and add them into the third qubit. So really just performing multiplication. And the reason for this, like addition, multiplication are universal classically, and codes are typically linear, so you can just add them for free. And similarly, like quantumly, if you add in a Hadamard gate, we get universal computation. So if we have a memory and we can also do fault-tolerant Toffoli or fault-tolerant multiplication, then like chances are we can probably get all the way to like universal computation. And so formally, what do we want? We just want some fault-tolerant gadget that like takes as input kind of 3 encoded states and outputs, say, the encoding of like x, y, and z, or 3 bit strings, and outputs encoding x, encoding y, and then adds the product of x and y, like the bitwise product of x and y, into z. So that's like what a fault-tolerant Toffoli would do, and just performing multiplication. And yeah, the problem is we don't know of like good quantum LDPC codes supporting a fault-tolerant Toffoli gate.
Sorry, can you say again the core challenge? I mean, this is a single gate, and if you corrupt less than, I don't know, a third, so if you corrupt not too many qubits, then it will fall in you know, it will be okay. So if it corrupt less than even a third or a sixth of the qubits, that's okay. So what's the core challenge here? I didn't understand.
Sorry, so we want a memory, so a quantum code that we can perform error correction on fault tolerantly. So like a way of, we first just want a memory, something that in which we can constantly store a logical state, even in the presence of like an almost linear number of adversarial errors at every time step. And then we also, on this memory, want to be able to do Toffoli gates on the underlying encoded logical states.
So the challenge is to come up with code on which you can do this, the Toffoli.
Yeah, on which we can both
The challenge is the code.
Yeah, it's a code that both has fault-tolerant error correction. So yeah, it has error correction and a Toffoli. And actually, either one we can get alone. So like LDPC codes give fault-tolerant error correction. There's like non-LDPC codes that have fault-tolerant Toffoli.
Okay.
But yeah, we don't know. It wasn't known like how to get both together. Thanks. Yeah. So what we're going to do is we're just going to come with a new quantum memory that actually does support fault-tolerant Toffoli. And it's not going to be, at least in the quantum case, it's not going to be a quantum LDPC code. So to see how we do this quantumly, it's actually good to go back to the classical setting, because classically it was basically already known how to do this, and it actually ends up being like an almost LDPC code. So how do we construct a classical memory with fault-tolerant Toffoli? Or actually, in classically, we can just say fault-tolerant multiplication. So we're just multiplying the underlying logical states. So first I'll define the code, the encoding. And we'll view the encoding takes in a message, which we just view as some multivariate polynomial over a finite field FQ, where we bound the degree of each variable to be some value k, where k is less than the field size. Then to encode this message, to encode this polynomial, we simply just write down the evaluation of the polynomial at all points in FQ to the t in our vector space. So we're just taking like a polynomial evaluation code. So the length of the code is q to the t. As long as q and t are kind of both growing with simultaneously, then q and t both are subpolynomial in n. If we choose parameters right, the number of logical bits is also almost linear. And this code actually has a lot of low weight checks. The restriction to every axis parallel line, just by definitions of multivariate polynomial, will be a degree k univariate polynomial. So that means that we can just check any q bits along a line, and we should see a low degree univariate polynomial, which means that we have a natural way of detecting errors. We just kind of run all these low weight checks, kind of in every direction. We check all the axis parallel lines. If we see a bunch of univariate polynomials, we know that we're a code word. If some of these lines don't have a univariate polynomial, we know that we violate some constraints. And actually, it's known, it was shown by Wiedermann that and also some other works in other regimes that this check, if we just kind of sample a random or kind of count the number of these checks that are violated, that will be a good approximation to the number of errors that occurred. So if we want to figure out if many errors occurred, we can just kind of count or sample and see if kind of most of these checks are violated or not. That's also another statement saying this code is locally testable. And it turns out that we can do even more. We can actually also perform low depth fault tolerant decoding. If we just in one direction at a time, going through the t directions, we just run a decoder within every column in that direction, a decoder for the univariate polynomial evaluation code. Then we can actually we can kind of decode in one direction at a time and ultimately correct whatever errors may have occurred on our code state. So it's long been known that this type of decoding will work if the decoding is noiseless. We actually also are able to show that even if errors happen during this decoding in one direction at a time, we still correct errors at a higher rate than they're introduced. So we still fault-tolerant error correction. There's a bit more work to be done there, but yeah, I guess intuitively you can see how the low weight checks are giving us this fault-tolerant error correction. So this is our classical memory. It also has this multiplication property that if we multiply two degree k polynomials, we get a degree 2k polynomial, which means that we can fault tolerantly perform multiplication because we just line up two code blocks and multiply them bit by bit, component by component. That's depth 1, so it's by definition fault tolerant. Not many errors can occur. But it does increase the degree. So as I'll describe later, we will eventually need to fault tolerantly reduce the degree back down to k to repeat this multiplication many times. Cool. So quantumly, we want to do the same thing. And basically, we're going to introduce some new quantum codes supporting both fault-tolerant error correction and fault-tolerant Toffoli. And what we're going to do here is we're going to do kind of exactly what you're always taught not to do with constructing quantum codes with low-weight checks. We're just going to impose the classical low-weight checks in both the x and the z bases. And kind of it's well known that a good quantum LDPC code consists of two classical LDPC codes, but they're actually bad classical LDPC codes. So if you take pretty good classical LDPC codes, like the one I just described, it's known that the checks in the x and z bases cannot commute. So you'll never get a good quantum LDPC code. And our key observation is it's actually fine. we actually won't need these checks to commute. So formally, like for some technical reasons, we're now going to take like a subcube of our entire vector space. But again, we're going to place our code components like in some high dimensional vector space. So the number of code components is just the size of this rectangle. The side length of the rectangle and the dimension grow subpolynomially in the block length. And then we just impose like checks in both, like parity checks in both the x and z bases that just require the restriction to each axis parallel line to be like a low degree univariate polynomial. So we just impose the exact same checks we had classically in both the x and in the z bases.
Sorry, do you actually mean x and z? So you're talking about a large field, right?
Yes. Oh, sorry, yeah. So everything here is like Pauli's over f cubed, so like Galois cubed it. It actually does generalize, everything generalizes if you define it, yeah. Thanks, yeah. Yeah, so I'm brushing over this a bit, but yeah, we are working over actually a very large field here, and I'll come back to that a bit. And so our check weight, these check weights, just like in the classical case, the check weight is subpolynomial. But these checks don't commute, which I guess if you were trying to make like good quantum LDPC codes, this would be a deal breaker. But for us, we just want a good quantum memory, so we're just going to say that's fine. We'll just like the technical term for this, like we call them like gauge operators instead of stabilizers. So just like non-commuting checks for our code. And we now just need to, I now like need to argue that like we can actually do fault-tolerant error correction on this memory. So we have these non-commuting, so we have well-defined checks. They don't commute. What does error correction look like?
So it's not a stabilizer code, basically?
Yes, it's a subsystem code. So it's like you can view it as a stabilizer code, which there's a larger code that's a stabilizer code, and then we're kind of at any given time working within a subcode, like a subsystem of the stabilizer code. And like, what does that look like in practice? You can think of it as kind of, it's a stabilizer code, yeah, exactly, where there's some logical qubits, and there's some additional things that are like basically logical qubits, but we're actually going to call them gauge qubits because they're actually not protected against errors. So we have these like gauge operators, which are like low-weight logical operators. They're kind of like low-weight corruptions that could corrupt some of our logical qubits. So we just kind of, we say, all right, for these logical qubits that can get easily corrupted, we'll just call them gauge qubits, and we just won't use them to encode the message. We'll only encode the message in the subset of like true logical qubits that we are going to use, and that we are going to protect against errors. And then even if we like have some physical errors, we'll just kind of measure the x checks, measure all the x checks at once. And this measurement procedure will measure these low-weight gauge operators, which could totally corrupt these gauge qubits. It could like project these gauge qubits into some arbitrary state in the x basis, but it will still preserve the logical qubits. And using these measurement outcomes, we can actually compute a Pauli Z correction that will correct whatever Z errors occurred. And then we'll do the same thing in the other basis. We could have like some x errors arising, but we'll kind of measure all of our Z checks, our Z gauge operators. This will, again, it will totally corrupt the gauge qubits, project them into some arbitrary state, but it will give us enough information that we can correct whatever x errors occurred and bring us back to our starting point. It is worth saying kind of like after measuring the x checks, we're able to fix these gauge qubits in like a plus state. After measuring the z checks, we're able to fix these gauge qubits in the 0 state, but we're never encoding our message in these gauge qubits. So unless we're doing some gate like a Toffoli gate where we actually will care about their value, oftentimes we don't care what value these gauge qubits have actually.
So where is it that you're gaining over regular quantum read Muller codes, where you basically do the same there that it does commute?
Great.
So the rate is slightly different, but is this where you're gaining?
It's the distance. So quantum read Muller, as far as I know, like never beat distance root n in both bases at the same time. Here we're able to get distance like almost linear in both bases.
But the rate is...
The rate is, I guess, probably almost linear in both, like almost linear number of logical
So
qubits.
if you could get good codes this way, would that lead to the parameters in your construction being better, like the PCP parameters?
Oh, I see. So right, so we can get kind of somewhat comparable parameters. Oh, I see what you're saying. Oh, sorry. There's like a lot of parameters in place. So I think part of the reason that these is the question like why do we get worse parameters than classical? Because I guess classically we had a polylog, and here we don't have a polylog. So I think an answer to that question is that quantumly, just the distance is always a little like you can't approach distance 1, like relative distance 1 quantumly. You can only approach relative distance 1/2. So when you take a high dimensional power, like for a classical code, you can start really high to 1 and stay pretty close to 1. Quantumly, you start at 1/2. So when you take a high dimensional power, that drops much more quickly. So yeah, so it seems like we probably could get back to polylog by doing some much more careful concatenation, but yeah, that's just kind of like some intrinsic thing that classically the relative distance starts at 1/2. Thanks. Right. So I did claim that kind of the key reason we're doing this is that we'll get like very high distance, and there's a couple things we need to do to make sure this memory is high distance, to make sure it can withstand like an almost linear number of errors. So one issue is that like the reason that people really like commuting checks, the reason that kind of people aren't doing this sort of error correction very often, as far as I can tell, is because like these measurement errors, they could cause since these measurements don't commute, like at every round we're kind of totally corrupting these gauge qubits, which means that we're like totally getting like different measurement outcomes at every time. So we can't just repeat our measurement outcomes until we kind of get like the same answer a bunch of times, then we're confident. And so in general, like when we have non-commuting checks, it's much more difficult to deal with measurement errors in order to compute the correct correction. And fortunately, we're actually able to solve this issue by observing, actually using an observation from a previous work with Venkat, that because these classical like multivariate polynomial evaluation codes are locally testable, like these classical product codes are locally testable, we can use classical local testability to correct any measurement errors that happen during our measurement of the X and Z checks. So actually, by classical local testability of these underlying classical codes, our quantum error correction procedure is fault tolerant. This is I won't have time to like get into exactly why this is the case. I can talk about it offline, but this is like somewhat surprising because it's saying like we're ultimately trying to construct quantum PCPs, and actually like classical local testability might be enough. Like we might never need quantum locally testable codes. We might be able to get away with like some classical locally testable codes within a quantum code construction.
Because of this gauge idea.
Yeah. Yeah, exactly. And I should also say, if you're familiar with like flow K codes, this kind of looks a lot like that. So we have kind of like a flow K-like error correction procedure, which is kind of interesting. Yeah.
So the logicals here actually evolve, or they stay the same?
The logicals stay the same. Yeah, only the gauge qubits. So I guess you can kind of view like all of our logical qubits as being divided into like true logical qubits that encode the message, and then gauge qubits, which are like logical qubits that don't encode the message, and only the latter change. Cool. So there is one more challenge, which is we still need to actually just prove that this code has good distance. So it turns out that like the reason the classical memory I described a few slides back just automatically has good distance is because we can view these multivariate polynomial evaluation codes as just products of univariate polynomial evaluation codes, like products of Reed-Solomon codes, if you're familiar with those. And kind of products of classical codes always have good distance if the underlying classical codes have good distance. But somehow when we take products of quantum codes, like when we have these quantum multivariate polynomial evaluation codes, it's not at all obvious that the distance of the product code grows as the product of the distances of the factor codes. In general, for a quantum product code, the distance of the product code could be anywhere between the product and the maximum of the distances of the factor codes. And actually, this kind of, I think, can only get worse as you go to higher dimensional products. Like we take a t-dimensional product, so then it's like a max of t things versus a product of t things. So actually, what we need to do is we need to kind of prove that this upper bound is roughly tight, that the distance of the product code is close to the distance of the factor codes.
Which product are we talking about?
Yeah, so it's a subsystem product. I intentionally didn't define it because it's a bit involved. So classically, it's just a tensor product of classical codes. Quantumly, so if you've seen like hypergraph or homological products, it's similar to that, but it's like a slight variant, like a subsystem variant with these gauge operators. And actually, everything I'm saying applies both to like these like tensor products of chain complexes or like hypergraph homological products, and also to the subsystem products. So basically, any kind of reasonable type of quantum code product that I've seen, like any sort of homological type product, I think will kind of have this property.
Is this the first time that subsystem codes, the product of subsystem codes was used?
So it's been studied by a handful of papers before. So actually, so this idea of like the fault-tolerant error correction and also just the problem of trying to use like products of algebraic codes with these subsystem products was in a work from like a year or two ago with Venkat. What we weren't able to do in this prior work was like show good distance of these high-dimensional subsystem products. So kind of the new thing is that what I'm about to describe, we're actually able to show that if we take a high-dimensional subsystem product of these polynomial codes, we still get like linear distance. But yeah, before that work, there was only like 1 or 2 papers looking at. It's somehow like not too well studied of a construction. Right, and so kind of what's the key thing? Like, how do we prove this distance upper bound? I guess I'm running out of time, so I won't like show exactly what the whole problem setup is and everything. I'll just kind of give you the answer, like what's the core insight, or like what's the core statement that we need. The core statement that we need is that if we take some like vector space over a huge field, I'll draw it in 2 dimensions, but really it should be like some higher number t of dimensions. Then if we fix some rectangle E, some n by n rectangle E, in like a smaller k by k pseudo-random rectangle A can be actually random or like appropriately pseudo-random. We want the property that over this huge field, for this appropriate choice of rectangles E and A, for every small set S inside E, we want the property that for a random low degree polynomial, like a random bound degree polynomial, the evaluation of this polynomial in S has no correlation with the evaluation of this polynomial in A. And like, why is this the property that we want?
How is A chosen?
A, so you can just choose it like randomly and fix it, and then, but actually we'll be able to de-randomize that. So you should think of it as like some fixed random rectangle inside a vector space over a giant field. And so intuitively, what we're going to do is we're going to define our polynomial evaluation code to have code components corresponding to points inside E, and message components, like logical bits, corresponding to evaluations inside A. So the evaluation of a polynomial inside A gives us the message, the evaluation inside E gives us the code word, and the polynomial degree is large enough that there's many code words, many valid code words corresponding to the same message. And then like the quantum encoding just uses like the superposition of all these valid code words for a given message. And so quantum code distance is equivalent to like local indistinguishability, which is just this property that if we want the property that if we kind of look at a small number of code components, we can't learn anything about the underlying message. So intuitively, that's why we want to prove this lemma, that like if we look at a small number of components of our code word, there is no correlation with the underlying message. And like we show that if the field is large enough and A is random or appropriately pseudo-random, this key lemma holds and then we get good distance. So I should probably start wrapping up soon. So I will just say kind of this is like the key engine that makes the whole construction work. Somehow like everything is built around like having this memory with Toffoli and with low weight checks. And to do that, we need this product. And then to get this product, we need good distance. So kind of this is really what everything revolves around. Cool. So I'll probably I should probably wrap up soon, so I might just speed through. Yes.
Maybe one question. So just, was the message that kind of like if you work with these low-degree polynomial codes, then the fault-tolerant top rate is like automatic, even in the quantum case? Or is it like, it did to work for that too?
Oh, thanks, yes. So, thank you, yeah. So it is actually automatic.
Okay.
It's something you have to prove, but it's like, it follows out from the definitions that since we're working with low-degree polynomials, kind of once we fix the gauge qubits in the right state, then we can kind of just perform a physical Toffoli gate, just line up 3 code blocks, perform a physical Toffoli gate across these 3 code blocks, and that will just automatically induce logical Toffoli on the encoded logical qubits. That's a good point. So we do get the Toffoli or multiplication for free, and yeah, so the upshot here is we've kind of constructed this memory that's robust and almost linear number of adversarial errors at every time step, and has fault-tolerant Toffoli. And even if you ignore the Toffoli property, I think this is already a really interesting memory because, as I mentioned before, kind of the only known quantum, like linear distance quantum memory previously was like these good quantum LDPC codes. This is, I guess, like a second construction of a quantum memory that's robust to a lot of adversarial errors, which already, that alone is, I think, a pretty interesting object.
Sorry, what is not transversal?
What is not transversal?
Yeah. Which of the universal set of?
Oh wait, so what's not so Hadamard is actually transversal, but when you do Hadamard, you change the code. You swap the X and Z bases. So then we're gonna need to like.
You do have degree reduction.
Yeah.
Okay, so it's not exactly transversal. You have to apply degree reduction at the end.
Oh yeah, so Toffoli is transversal if we fix like these 2 code blocks to be degree K and this one to be degree 2K.
Yeah, okay.
Yeah, but yeah, we will definitely need degree, yeah. I mean, Ethan Cannell still holds, so.
And you do it as an AB?
Oh, I'll maybe flash up. I'm running out of time, but yeah, so that's the last thing I wanted to talk about was how we do degree reduction. So just to really kind of summarize what we've seen so far, so like exactly what Dorita's saying is where we're going. So we've seen how to do error correction and fault-tolerant Toffoli. What's left is like kind of addressing the Toffoli. So if we don't want to do it just across 3 code blocks lined up, but to do arbitrary Toffoli gates, we need to do that. Also, like as Dorit pointed out, kind of we have some differing degrees in our 3 code blocks. So we'll need to reduce the degree of this code block if we want to do Toffolis in a different way. And also, when we do a Hadamard gate, we do Hadamard gate on the entire code block, but we swap the 2-factor codes. So we're going to need to like swap our code back. And basically, all these remaining problems are solved by code switching. Like if we can switch from like degree K to degree 2K or swap the X and Z codes, then we can switch between different codes and solve all of these issues. And the picture for code switching is this. We just view our codes I've described as being encoded in a product of individual Reed-Solomon codes. And then we can, in any given direction in time, we can like unencode all the code, like all the columns in that direction, or re-encode back in that direction. So we can kind of unencode out of C3, we can re-encode into C3 or into a different code. And when we do that, kind of errors only propagate within columns. So this is like still pretty fault tolerant, this code switching procedure. And the nice thing about that is if we code switch in all the directions, like one at a time, like first in one direction, then another direction, then a different direction, we can swap out the factor codes one at a time. So we can just, once we do this in all the directions, we can change the code degree, swap the X and Z basis codes, and so forth. And we can actually even do more. We can do transversal gates in these intermediate stages when we're decoded out of one of the codes, which means we can actually choose which direction we do our Toffoli gates in. So we can do Toffoli gates not on the entire code block, but on these like hyperplanes, these smaller code blocks. So to summarize, we have a memory, and we can do transversal Toffoli and transversal Hadamard in these hyperplanes, where our qubits are arranged in like a larger hypercube. And this is actually enough for universal computation. Kind because it turns out it's known that like with Toffoli gates and like being able to perform Toffoli gates in one direction at a time on these hyperplanes, that's actually enough to like sort our qubits. So to rearrange our logical qubits to any arbitrary configuration. And this sorting is like polylog depth, so we can just like kind of run a sorting network, stick our qubits wherever we want them, so that then we can do a transversal Hadamard or a transversal Toffoli gate. Then we'll again repermute our qubits for the next layer of gates, do a transversal gate, and so on.
In between, it's still checkable. After one of those levels, it's still in an error correcting code that you can correct.
Oh yeah, so at every step, so each of these steps is an error correcting code, and then each layer is like the same code, but one dimension, like t minus 1 dimension instead of t. So yeah, we're always encoded in like a high distance code. Great. And I mentioned we need to do this over huge alphabets for the distance analysis. We use some recursive simulation to reduce the alphabet size. Intuitively, it's not a problem. It ends up, this is what's responsible for our n to the 5th space overhead. Yeah. So just to summarize, our main results were kind of in both the classical and quantum settings, a compiler from a logical circuit to a fault-tolerant physical circuit that withstands an almost linear number of adversarial errors at every time step. In both cases, our memory was a high-dimensional product of Reed-Solomon codes, these multivariate polynomial evaluation codes. In both cases, we used just transversal gates with code switching. And we get inverse polylog soundness classical PCPs and like conjecturally quantum PCPs. Cool.
Can you say a word about how to move from n to the one on the lower one to inverse polylog?
Maybe offline. It's somewhat involved. It's just kind of accounting more carefully. And so we have this like recursive alphabet reduction. It seems like if you kind of essentially like take this product more carefully and kind of recursively compose at the right time, there's a good chance that things would work out, but we haven't worked out all the details. Yeah, maybe I can say more offline. It gets a bit like hairy.
There's a question from the telegram.
Oh, sorry.
Is the alphabet e to the n to the 100 or like n to the 1 over 100?
Sorry, n to the...
Is it like poly n where the alphabet size? Is it exponential in poly n where it's like n square or n to the or
so
root n?
Initially, it's exponential in poly n. Where I think, so it depends which n in the... I think it's roughly exponential in the number of physical qubits.
I'm asking because classically, when you build PCPs, like there's no point in getting alphabet size which is that large, right? Because you could just combine all your variables into one, and then it's trivial.
Right. Oh yeah, yes, that's a good point. Sorry. So it's just small enough that we're able to. It's a good point. It's just small enough that we're able to make progress. Okay. So sorry, I'm forgetting the parameters, but I remember. Yeah, this is an issue, and it's like in every step of composition, we're kind of able to like take a square root in like the number of bits we need in a single alphabet symbol. So yeah, no. So this is a really good point. Oh yeah, sorry, I'm forgetting the exact parameters, but I think it's like if the... Oh yeah, maybe we can talk offline. But yeah, it is, yeah, that is an issue and it's like just small enough. Cool, so I did want, I said I would like have a slide on like the labor. That's what this is. So it turns out that like proving this stuff is really messy, and just to give a flavor of like what actually happens when you read one of these fault tolerance proofs. So you need a lot of data for every fault tolerant gadget. You need to specify the logical circuit, you need to specify the physical circuit, you need to specify the set of errors, like faults, that you can correct, that like the set of faults that are allowed to happen during the execution. And then you need to specify the input and output codes. And for each of these, you need to specify a code and coding map. Again, a set of correctable errors. and also what values your gauge qubits have. And then you like take these objects which have all this different data, and you start like composing them. Like you compose them sequentially in parallel, simulatively, like recursively. And somehow there's just like a lot of finicky things that come up, and we really heavily relied on these ideas on this paper by Quinn and Chris, and then a follow-up that also had Sunny on it, that really kind of carefully thought out like what are good ways to kind of set up this data and compose this data in ways where we can actually prove fault tolerance. So I don't know. This is just like a remark on like actually proving all the stuff I described. The proof will look a little different than the description, but ultimately it's just kind of capturing the intuitive picture. But yeah, there are a lot of really subtle things that come up that I won't even talk about here, that I could talk about offline, that are actually somewhat surprising when you really try to prove quantum fault tolerance. So that's kind of fun. Cool. So I'll just wrap up with a conclusion and outlook. So on the fault tolerance side, like good QLD PC codes gave linear distance memories, and the ideas are now really starting to take hold in practice, even in like companies that are trying to build quantum computers. They're trying to build these, and like industry labs are trying to build these QLD PC codes. But really, we don't just want to create, like, we don't want codes, we want whole fault tolerance schemes. And so, especially if we could reduce the space-time overhead of our scheme, maybe the ideas could also trickle into practice. On the PCP side, so the whole point of this talk is that fault tolerance gives a perspective, I don't know if it's a new or old perspective, on PCPs. We saw how classical PCPs can be obtained from classical fault tolerance, how hopefully quantum PCPs can be obtained from quantum fault tolerance. The key bottleneck for the quantum PCP setting question was the circuit Hamiltonian conjecture. And I will just say that it does seem like this fault tolerance perspective can be taken just beyond like what I talked about here. So for instance, I think kind of in Quinn's talk later this week, we'll hear about PCP gap amplification, and you could try to think about that maybe as amplifying the fault distance of a fault tolerance scheme. You could also think about like specific questions in the PCP literature, like the linear size PCP question. You can look at analogous questions in the fault tolerance literature, like can we perform quantum fault tolerance with constant space-time overhead? And somehow, I'm not an expert on linear size PCPs, but somehow these two questions seem to run to a very similar bottleneck, which is like kind of being thought about in these two like totally separate communities. So there might be more that you can learn by like kind of taking this connection between fault tolerance and PCPs seriously. So that's all I got. John Mentini?
Can you say anything about the relationship between the classical PCP that you get and just like the standard algebraic PCP? Like, are they both the same thing but under different perspectives, or?
Yeah, no, that's a great question. So I think ours there are some classical PCPs out there, like if you're familiar with like the Ben Sassen Sedan construction of PCPs and PCPPs, that have a lot of similar ingredients. I don't think like our PCP is literally the one written down in any papers, but the ingredients like these high like multivariate polynomial evaluation codes are quite similar. Some of them feel like a little bit different. Like I think previously people would really look at like arithmetization, and we're kind of replacing that with fault tolerance. So like kind of the core ingredients are the same, but the way you put them together is a little bit different.
You said a bit earlier that like labor was the reason that you didn't write down the control sum. So if you elaborate on how like your last slide connects to the control sum.
Oh, sorry, which slide?
The
This slide?
one where you said it was difficult to prove fault tolerance.
Oh, this?
Or like in general, what was the reason that you didn't write the control sum?
Oh yeah, so there are some like so I mentioned like we use side classical computation as noiseless. In the PCP setting, you don't want to allow that because that doesn't fit into this circuit Hamiltonian mapping. But you are allowed to just detect errors and abort. So instead we want to write like an error detecting version And that actually changes, like we kind of recursively compose these schemes that use some classical computation. We instead want to recursively compose error detecting schemes. And that also, like, there's some technical reason that in the alphabet reduction that will change like the Hadamard gate. So there's like a lot of pieces that you just have to swap out. And just, I mean, it's just a lot of, like, this thing is like over 100 pages just to like write the proof. And so it's like another 100, 150 pages, like it's just pure labor. Maybe something goes wrong. I wouldn't expect that, but yeah, it's like enough things change that I wouldn't know how to do it without rewriting like a substantial part of it.
So the major difference is the error detection.
Yes. Yeah, 'cause we want to get rid of the side classical computation, and we're able to do that. It seems like we should be able to do that by using error detection instead of error correction.
Wait, I have a maybe silly question. When you said labor, I thought you were going to say something about LLMs. Is it actually possible to automate any of this stuff, or do you have to like really, like by hand, like check every proof? Like, is the abstraction good enough to like automate thinking about it? I guess.
I mean, so it is like there are formal statements. Like in theory, there's nothing stopping an LLM from doing this.
But like when you actually did it, you did it by hand.
Yeah, I think my issue is these proofs are, I think, pretty painful to write and even more painful to read. So I actually just, like, it's very easy to write a fault tolerance proof that looks totally correct to experts and has a very subtle bug. And like, I think every time I've written a fault tolerance proof, the first version, there's something wrong and I need to take things apart. I think this is pretty hard. And so, not necessarily that a human is better than an LLM, but I'd feel better if I wrote it than, like, it's, yeah, just, it's finicky. But like, hopefully it would be really nice if in the coming years LLMs get good enough where they can do this better, and then we can just, I want to just tell them what's in this talk and then say, formalize this. That'd be fun.
More questions? If not, let's thank Louis again and. Can I say that again? I guess